The sequence begins with a breakdown in situational awareness. On an interception vector, a fighter pilot commits to a low-speed target, narrows his visual scan, and bleeds kinetic energy to match the engagement. Classic target fixation. Locked forward, he settles into a predictable line that secondary threats can exploit in seconds. The objective is to reconstruct the procedural chain that forced a Mitsubishi A6M5, a Model 520, out of the sky, creating a forensic anomaly that would remain unresolved for decades. The operational timeline anchors on June 19, 1944. The theater is the Philippine Sea, west of the Mariana Islands, near Guam. The broader engagement is recognized as a massive aerial clash between opposing naval fleets. Japanese aviation units are attempting a coordinated strike against United States Navy carrier strike groups. The Model 520 is flown by a Japanese Navy pilot identified in some later accounts as Shinya Ozaki. His immediate tactical objective is a low-speed rescue aircraft. A United States Navy seaplane engaged in air-sea rescue working to retrieve a downed aviator from the ocean surface. Ozaki initiates an offensive attack profile against this isolated, slow-moving contact. To properly engage the rescue aircraft, Ozaki has to pull power and bleed velocity, matching the target's lower energy state. That choice compresses his options. The Model 520 was engineered for extreme maneuverability and minimal structural weight, with far lighter protection than most American carrier fighters. With his attention fixed forward on the kill, the defensive scan collapses, just long enough for another aircraft to solve the intercept. This operational blind spot is exploited within moments. A United States Navy F-4U-2 Corsair night fighter, commonly credited in later accounts to Lieutenant Commander R.E. Harmer, establishes a tracking solution on the stabilized Zero. The Corsair possesses a significant speed, weight, and firepower advantage over the lighter Japanese aircraft. Harmer maneuvers into an optimal firing geometry while Ozaki remains entirely focused on the observation plane below him. The resulting engagement is brief, violent, and structurally decisive. The Corsair delivers concentrated machine gun fire directly into the flight path of the Zero. The incoming rounds immediately compromise the forward engine section of the Zero. The technical consequence is an unrecoverable decay in propulsion. The radial engine suffers catastrophic internal damage and instantly begins streaming heavy smoke backward along the longitudinal axis of the fuselage. The aircraft is now bleeding kinetic energy far faster than the failing power plant can generate thrust. Ozaki is forced to immediately abort the attack vector. The tactical reality shifts from an offensive strike to an extreme survival constraint. The airframe is critically crippled, suffering from terminal propulsion loss, yet the aerodynamic control surfaces remain responsive to pilot inputs. The pilot retains enough authority to fly the controls, but only as a glider. The engine failure sets a hard limit on remaining minutes aloft, with no capacity to reach a carrier deck or a secure operating base. He turns out of the fight toward the nearest landmass and commits to a dead stick descent, dragging a dead propeller and ruined radial engine at the nose. The shrinking glide radius leaves a single workable approach, terminating roughly 1.5 miles from the active runways of Agana Airfield. A hard concrete runway sits within sight, but the surrounding topography is dense, waterlogged tropical swamp, forcing an immediate survival trade-off. Attempting a dead stick landing on concrete without power is a structural gamble. Dropping the landing gear would add drag and could bleed away the last controllable airspeed before the runway threshold. Keeping the gear retracted on hard concrete would turn the belly into a grinding sled, tearing skin and lines and risking ignition from residual vapors. Under those constraints, the pilot deliberately turns away from the airfield and commits to the soft swamp. This decision initiates a kinetic bleed belly landing. By keeping the landing gear completely retracted, the pilot ensures the underside of the aircraft remains an entirely smooth surface. If the gear were deployed in soft terrain, the struts would immediately dig deep into the mud upon contact. Those embedded struts would act as fixed pivot points, violently flipping the massive tail section over the nose and instantly crushing the cockpit area. Instead, the pilot brings the aircraft down perfectly flat into the thick vegetation and wet soil. The soft mud functions as a continuous viscous brake. As the smooth duralumin belly contacts the swamp, it acts like a sled, in distributing the massive impact forces evenly across the entire lower surface of the airframe. The dense medium absorbs the forward momentum over an extended horizontal slide. This controlled deceleration profile dissipates the kinetic energy gradually, preventing the main wing spar from snapping and keeping the central fuselage completely intact. The aircraft successfully sheds its forward velocity and comes to a complete halt deep within the swamp. Once the slide ends, the dead weight of the engine block pulls the nose down, packing thick mud into the cowling, equipment bays, and seams along the belly. That burial conceals the wreck and reduces airflow and sunlight at exposed surfaces, conditions that can slow some forms of deterioration and help protect markings and platees, even as wet, salty soil continues to attack metal over time. The swamp is less a clean vault than a smothering cover. It hides the fighter, buffers it from exposure, and makes it hard to spot from the surface. What localized condition prevented post-war cleanup crews from spotting an airframe buried just miles from the active perimeter? About 18 to 19 years separate the moment the airframe settled into the mud from its accidental rediscovery in the early 1960s. Accounts vary, most often placing it around 1962 to 1963. During this extended period, post-war clearance and scrapping removed wartime material that was visible, accessible, and prioritized for safety and redevelopment around active facilities. This wreck, buried and overgrown just outside a highly active military zone, never presented an obvious surface target. The isolation boundary was finally breached by chance when a local government worker operating heavy brush clearing equipment near the swamp edge in that same early 60s window stripped away the vegetation shield. Tasked with expanding the cleared zones, the machinery forcefully stripped away the dense vegetation shield. The heavy equipment was designed to tear through thick roots and soil, possessing enough torque to easily crush an aluminum fuselage into unrecognizable scrap. As the steel blades pushed deeper into the overgrown sector, the operator spotted a large metallic structure embedded in the undergrowth. Recognizing the shape of an aviation wing root, the operator halted the heavy equipment immediately, preventing accidental mechanical destruction of the fragile aluminum skin. This immediate operational pause preserved the site for formal military evaluation, shifting the event from a land clearing operation to a controlled historical investigation. Arriving military personnel found an incredibly intact artifact. The surrounding mud had shielded much of the lower duralumin structure from catastrophic surface loss. Above the mud line, the heavy jungle canopy had deflected direct ultraviolet light in severe weather systems, preventing the surface paint from completely bleaching or flaking away. The investigators visually confirmed the original dark green factory paint still clinging to the upper fuselage and wing surfaces. More critically, the large red circular Hinomaru markings remained clearly identifiable on the wings and fuselage sides, instantly confirming the aircraft as an Imperial Japanese Navy fighter. Recognizing the historical significance, personnel initiated strict in situ stencil validation. Before attaching any tow cables or attempting to shift the heavy airframe from its resting place, investigators meticulously documented the external markings exactly where the aircraft lay. Moving a corroded airframe risks snapping the thin aluminum panels that hold vital historical data. The forensic discipline of reading the plates prior to extraction ensured that even if the tail section collapsed during lifting, the historical provenance was already secured. By carefully clearing the immediate surface dirt by hand, they exposed the vertical stabilizer. Painted clearly on the tail section was the code 43-188. That marking is often interpreted as consistent with assignment to the 343rd Naval Air Corps, though tail codes alone are not definitive without supporting records. The forensic team then focused on locating the primary manufacturer data plate, the factory stamped tag that can anchor the entire case. Working in situ, they found it on the fuselage, cleared away the built-up grime, and read the markings before any heavy handling could destroy them. The plate matched a Mitsubishi A6M5, a model 520, with factory number 4685. With that identity captured in notes and photographs, the next problem was purely mechanical: how to separate a fragile airframe from mud that had held it for nearly 2 decades. Extracting a duralumin airframe from deep mud is a mechanical trap. Waterlogged compartments add weight, and the swamp grips the structure like a suction vise. Any hard pull on a tail or wingtip can shear fatigued metal. The crew has to clear what it can, rig support under the strongest central members, the wing center section, and forward mounting structure, and then bring tension on slowly, easing the wreck free without shocks. As the aircraft breaks the surface of the swamp and clears the physical boundary of the mud, the full structural condition becomes visible. The rigid aluminum frame demonstrates remarkable survival, holding its overall aerodynamic shape perfectly intact. However, the extrication reveals a distinct material vulnerability. While the metallic surfaces resisted complete destruction, the organic components did not. The fabric covering on the tail rudder is entirely missing, rotted away by decades of biological activity within the jungle environment. Only the bare metal ribs of the control surface remain attached to the vertical stabilizer. This absence of fabric serves as a clear physical indicator of the aggressive environment the airframe endured, contrasting sharply with the survival of the main metal fuselage. With the physical extraction complete, the artifact immediately faces a severe chemical threat. Pulling the aircraft out of its sealed, wet environment triggers flash oxidation risk. For nearly 2 decades, the dense swamp mud blocked atmospheric oxygen from reaching the bare duralumin, artificially stabilizing the galvanic corrosion cycle. By lifting the airframe into the open air, that protective anoxic seal is violently broken. The saturated metal is suddenly exposed to high concentrations of oxygen and ambient tropical heat. If left untreated in this transitional state, the moisture trapped inside the microscopic pores of the aluminum will react with the open air. This transition can accelerate corrosion and surface breakdown, undermining strength and fine details within days to weeks if stabilization does not begin quickly. The recovery team must execute immediate stabilization protocols to secure the extricated fighter. The entire airframe requires thorough washing to purge the acidic swamp mud and biological debris packed inside the fuselage bulkheads. Workers must manually clear the heavy soil from the internal wing roots and the cockpit flooring to shed the destructive trapped moisture. Once the heavy soil is removed, specialized inhibitors must be applied to displace the remaining dampness and seal the vulnerable aluminum skin against the atmosphere. This critical procedural step neutralizes the aggressive oxidation cycle and places the metal back into a chemically stable baseline. Only after the rapid degradation threat is fully arrested can the artifact be safely transported away from the immediate recovery zone. With the airframe successfully pulled from the swamp, what engineering path would guarantee its long-term survival? The physical stabilization of the extricated fighter forces an immediate engineering trade-off. The artifact is chemically secure, but the structural reality of the airframe demands a definitive operational pivot. The recovery management team must decide between pursuing an airworthy structural rebuild or limiting the project strictly to historical preservation. This decision hinges directly on the mechanical condition of the original factory materials and the irreversible effects of long-term environmental exposure. While mitigating the immediate flash oxidation risk successfully halted active corrosion, the extended burial period exacted a permanent microscopic toll on the duralumin components. Engineering evaluations reveal extensive material fatigue hidden deep beneath the stabilized outer skin. The main wing spars, engine mounting rings, and primary load-bearing bulkheads have lost their original tensile strength. The crystalline structure of the vintage metal has become fundamentally brittle due to age and dormant galvanic action. If mechanics attempted to subject this airframe to the severe aerodynamic stresses of active flight, including heavy engine vibration and high positive gravity loads, the compromised internal structures would instantly fracture. To achieve an airworthy status under strict aviation safety regulations, engineers would be forced to dismantle the entire fuselage. They would have to drill out thousands of original rivets and discard the fatigued internal framework. The team would need to fabricate entirely new structural sections using modern aviation-grade aluminum to guarantee operational safety. This highly invasive process creates a severe historical paradox. By replacing the original material solely to make the aircraft fly, the engineers would effectively destroy the very historical integrity they just recovered. The resulting machine would become a modern replica wrapped in a vintage outer skin, fundamentally erasing the authenticity of the specific artifact. To prevent this irreversible loss of historical data, the project is strictly constrained to a static restoration limit. The engineering decision dictates that the airframe will be cosmetically returned to its original exterior configuration, but will never again be subjected to aerodynamic or operational loads. This framework allows conservators to repair superficial surface damage, reconstruct the missing fabric control surfaces, and reapply accurate exterior coatings without replacing the fatigued internal skeleton. The original factory duralumin, the verified data plates, and the underlying structural configuration are completely preserved as a coherent, non-load-bearing display piece. With the restoration parameters permanently locked, the operational focus shifts entirely to complex transoceanic logistics. The United States military must safely transport the delicate, statically stabilized airframe across the Pacific Ocean without inflicting further mechanical damage. Shipping a brittle, assembled aircraft requires rigorous physical preparations. The recovery team must construct a custom handling cradle designed to distribute the static weight of the airframe evenly across a transport deck. This cradle prevents the brittle wing roots and the compromised lower fuselage from cracking under their own weight during transit. Ocean transit introduces a new array of environmental and mechanical hazards. The continuous rhythmic vibrations of a massive cargo vessel engine, combined with the heavy torsion forces generated by ocean swells, threaten to warp the unsupported tail section. To counter this, riggers must implement a rigid securing plan, bracing the fuselage and locking all remaining control surfaces into fixed positions to prevent wind or motion shear. Furthermore, the exterior must be shielded from the highly corrosive salt air environment of the open ocean, requiring protective wrappings over the freshly stabilized metal. The meticulous logistical planning culminates nearly 2 years after the initial extraction from the swamp. By early 1964, arrangements are made to ship the secured aircraft from Guam back to Japan. That movement marks the transition from a raw field recovery into a formal restoration and custodial process. The trans-Pacific journey represents a significant logistical achievement, moving an extremely fragile, non-structural artifact thousands of miles across open water without compromising its meticulously preserved state. How would this statically restored fighter transition from a recovered relic to a formal diplomatic transfer? The next obstacle is procedural, not physical, transferring a former combat aircraft across borders and into lawful custody. In mainland Japan, conservators completed the cosmetic work documented at recovery, rebuilding the missing fabric control surfaces over the surviving tail ribs and finishing the camouflage in dark green over gray. With the restoration complete, administrators executed the chain of custody requirements to move the airframe from U.S. control to the Japanese government. And that meant formal reclassification from captured enemy salvage to a recognized historical monument, certification that it was demilitarized and cleared of residual hazards, and transfer agreements that addressed liability tied to an unairworthy structure. By late 1964, often reported as November 3rd, the protocol was finalized and the fighter formally entered Japanese custodial control, closing the long discontinuity in its record. The Japan Air Self-Defense Force assumed stewardship and transported the artifact to the Hamamatsu Air Base Museum. To protect fatigued duralumin from decades of point loading and to reduce accidental impact damage at floor level, the museum favored a suspended display supported at conservative load points. In 2024, the museum announced a relocation and repair project intended to revise how the aircraft is presented, so visitors can view it more closely while maintaining safe support. The original factory data plate recorded as 4685 remains a key piece of physical evidence, the final, immutable proof of a disciplined historical extrication.